So today what I'm going to be presenting on is improved temporal focusing at the source location by using deconvolution. And what I'd like to start off with is really discuss the motivation. And this was all a joint project done with Ernst Niner Leitinger, who was a visiting researcher at CWP from the German research lab Bonn. So the motivation behind it. Well, in order to do that, let's look back at time reversal. So time reversal has been the focus of much research due to its ability to compress a wave field at a point in both space and time. This has led to it being used in a wide variety of applications, such as communication, non-invasive surgery, seismology, and non-destructive evaluation. Now the problem though with time reversal is that in a real-world experiment, it's not able to generate a perfect direct delta function focus due to certain conditions not upholding. In order for it to work perfectly, you need to have no attenuation present within your medium, you need to record infinite bandwidth, you need to have full aperture of your wave field, or in other words, full coverage. And obviously those things don't happen. So what we wanted to do was we just wanted to look into a simple method to try and improve the temporal focusing at the source location. So what we looked into was deconvolution. And what deconvolution says in the time domain is that we have a recorded signal R of t convolved with our back-propagating signal G of t, and we said that this is approximately equal to a direct delta function. Now when we bring this into the frequency domain, our convolution just becomes a multiplication, and our direct delta function just becomes 1. So then we go ahead and we solve for G omega, and this solution you guys have all probably seen before, where we have the complex conjugate of R of omega in the numerator, and we have a stabilization term epsilon in the denominator that we've added such that for the cases where R of omega might equal 0, when there's noise present. If R of omega is equal to 0, you're essentially dividing 1 by 0, and so your signal would blow up, we wouldn't get a very good focus. The stabilization term epsilon, we say, is equal to just a constant scalar factor gamma times the mean of R omega squared. And one of the things we'll play with today as well is to play with this gamma value and see how it affects our focus. What's important to note though too about this method, it's very simple. We apply this equation to all our receivers the same way. And this is different from what you're about to see from Farhad after me, who really works on trying to generate the most optimal focus possible by weighting receivers differently and really trying to improve the spatial focus as well. Our main goal is to try and keep it simple and just focus on improving the temporal focusing. So first what I'd like to show is the first experimental joint project we did with Los Alamos National Laboratory. And this is kind of an introduction as a leadway into the big project we did with Ernst Niner Leitinger. So this project with Los Alamos had the following experimental setup. We had an irregularly shaped aluminum sample of approximately 1,000 cubic centimeters. We then did a reciprocal time reverse experiment where our source was a transducer and our receiver was a laser vibrometer. Now the downside to using a laser vibrometer as our receiver was that it couldn't act as both a source and a receiver. That's why we did a reciprocal time reverse experiment. Now the benefit though is that we could use it to scan around our focus at the time of focus to also measure spatial focusing capabilities of our method. But we won't be discussing that today here in this presentation. What's also important to note is that this experiment had our source and a receiver on the surface of our irregular shaped sample, which will be different with the new experiment I'm about to introduce. So finally, this was an ultrasound experiment with the source function having a central frequency of 200 kilohertz. So we propagate our source wave field from our source transducer and record it. We then apply time reversal and deconvolution to that recorded data to get the following back-propagation signals. In the top, in blue, is shown time reversal's back-propagating signal. In the bottom, in red, is shown deconvolution's back-propagating signal, with the x-axis being time, y-axis amplitude. You can note a clear difference between the two signals, where deconvolution has also added now information past 1.64 milliseconds. We had found in previous experiments with Los Alamos that this was necessary to generate a symmetric-like focus. If we calculated for this red deconvolution coda, and then arbitrarily set after 1.64 milliseconds equal to 0, we would still get a focus, it just wouldn't be symmetric. So now we take these back-propagating signals, and we're going to propagate them through our medium again, and look at how the temporal focus is compared. And more specifically, we're going to look at how those temporal focuses compare to our original source function. So here you'll see the focuses at the time of focus. So our wave field as a function of time. In black is our original source function. In red is a temporal focus achieved using deconvolution. And in blue is a temporal focus achieved using time reversal. What you'll note is that time reversal has significant side lobes present away from the time of focus, whereas deconvolution's temporal focus does not. This allows deconvolution to generate a much better focus and able to reconstruct our original source function. And we want to quantify this. So what we did was we created a window around the time of focus such that we had 100% of the energy of our original source function within this window, as such. We then looked at how much energy was within this window compared to our whole wave field recorded for our deconvolution and time reversal's temporal focus achieved. What we found out was that deconvolution had 70% of its energy within this window, whereas time reversal only had 15% due to those significant side lobes present within time reversal's temporal focus. Thus we were seeing a significant improvement in temporal focusing capabilities by using deconvolution for this experimental setup. So this is all kind of the introduction. This is what we had done with Los Alamos 2 years back. But now we've done a new experiment with Ernst Nieder Leitenkler, and we've actually done this at Mainz in the civil engineering lab. We started all the way from scratch, building the sample, everything ourselves. The main goal now for this experiment was to not only embed our sources within our sample itself, but to also look at the application with multiple sources. Because we would like to apply this towards microseismic event locating. And we know that with microseismic events, we're going to get hundreds and thousands of events in our recorded coda. So we need to make sure that this works for multiple sources that are emitted at different times as well as same times. But before we do that, we need to just test that it worked for this experiment. So this is the setup we have. You can note in this figure 3 transducers. These transducers are attached to a steel frame. One of the transducers, transducer number 3, is oriented orthogonal to the other 2 transducers. We then place this steel frame with our transducers inside concrete. Generate the following concrete block. We then place our receivers on the surface of this concrete block itself. So now our idea is, let's propagate our source wave fields from our embedded transducer, propagate it through our concrete block, and record it on the surface transducer, so our receiver. Then apply deconvolution and time reversal to that recorded data, and now actually physically back-propagate it from our surface transducer, our receiver, turning that into a source now, and then turning our embedded transducer into a receiver at our original source location, looking at how the wave field focuses there as a function of time. So let's first look at our test experiment, making sure that this works now for a completely different experimental setup than we had done with Los Alamos. So now we just use only a single embedded transducer as a source, propagate our source wave field, record it on the surface of our concrete block, and then apply both methods. So this would be our original recorded data. What you'll note here is that there's this low frequency noise present. And there's actually a lot of different noise. Depending on what time of day and who was in the lab, we'd have different kinds of noise going on. Because it was done in the civil engineering lab, so our neighbors were running all these pumps and things like that. It was not very ideal experimental setups. But what's really great to show the robust characteristics of not just time reversal, but also deconvolution, is we actually ran a whole experiment with this recorded data that had all kinds of noise in it, not putting any single bandpass filter on it. We applied both methods, physically backpropagated, and looked at how the focuses compared, and we were getting just great focuses for both of them. So that showed that it worked even with so much noise present. But to make it all look nice, I'll just filter out the noise for you for these figures that I'm about to show you now. So this is our recorded data that we would use from now on to apply deconvolution and time reversal. So this is again for a single source at our receiver location. Now we're going to apply time reversal and deconvolution and get the following result. In top, in blue, is time reversal's back-propagating signal. In bottom, in red, is deconvolution's back-propagating signal. You can again see similar characteristics as with Los Alamos, with added information past 8 milliseconds. It seems a little bit different, more complexity to it. We're now going to take these two signals and physically backpropagate them from that receiver location. We're going to now turn that embedded transducer into our receiver and measure the wave field as a function of time, thus measuring the temporal focus. These are the temporal focuses we achieved at that embedded transducer. Even with all the noise, non-ideal situations, this is what we got. Deconvolution significantly, again, improved the temporal focusing compared to time reversal. Time reversal shows significant side lobes present away from the time of focus, whereas deconvolution does not. Just like we were seeing in Los Alamos. And now for a completely different setup, with embedded transducers instead of on the surface of our sample. We want to quantify this improvement again. So what we did was we again created a window around the time of focus, and we looked at how much energy was within this window compared to the whole wave field recorded. We found out that for deconvolution, we had 80% of the energy within this window. Whereas for time reversal, we had 40%. So we're getting a twofold improvement now for this embedded source setup and trying to make it more realistic. Well, more towards, hopefully trying to apply towards microseismic event locating. So that was our single source experimental setup, and we were quite excited about those results. Next, what we wanted to do before going towards testing multiple sources was just make sure that we really understood the impact of that regularization term. And this should hopefully be straightforward, and our theoretical expectations should hold for the experimental setup. So what do we expect? Well, here is our result that we got for a deconvolution signal with that stabilization term epsilon. Now, I had stated that the importance of that epsilon term was necessary for those cases where R of omega might be equal to 0. Because if our epsilon term, or stabilization term, essentially becomes 0, then the noise starts to impact our signal, and it really deteriorates our temporal focus that we are able to achieve. Now, if we improve our epsilon term dramatically, pretty much going to infinity, we expect that as the limit of epsilon goes to infinity, using just Taylor series expansion, we would just get a scaled version of our time reverse signal. So we'd expect our temporal focus using deconvolution now to just be almost identical to time reversal's achievable temporal focus. So what we did was we ran this for a single source type experiment. We had one transducer, just one single transducer embedded, emitting a source wave field. We'd record it on the surface of our concrete block, then apply time reversal, and then apply deconvolution 7 separate times with a different gamma value, going from a very small gamma value to a very large gamma value, and looking at how the temporal focuses compared. So here are the temporal focuses at that embedded transducer for these different iterations, different runs. In the top left, you'll see small gamma values. In the bottom right, you'll see high gamma values. In red are our deconvolution's temporal focuses. In blue are our time reversal's temporal focus. So let's first zone in on the low gamma value. So for this low gamma value, you can see we were getting exactly what we expected. More noise is starting to be incorporated. Our temporal focus deteriorates. Now, as we increase our gamma value, we start approaching this optimal focus, where we're suppressing more and more of these side lobes and generating a nice, cleaner temporal focus. Now, if we go to the other side of the pendulum and continue to increase our gamma value, going towards the bottom right figures, you can note that deconvolution's temporal focus, shown in red, approximately looks like time reversal's temporal focus. They look very similar. So again, that was exactly what we had predicted theoretically to happen as well. But we want to visualize this differently because you might not be able to see very clearly what I was trying to explain to you verbally. So what we did was we again created this window around the time of focus and looked at how much energy was within this window compared to the whole wave field recorded, and plotted that temporal focus as a function of gamma to create the following plot. So as we decrease our gamma value, you can see that our temporal focus drops off very rapidly. Now on the other side of the spectrum, as we increase our gamma value, we don't drop off our temporal focus as quickly. Rather, it goes down very slowly. Now here's one of the mistakes I made when I was designing this experiment, is I should have kept going, increasing the gamma value. Because what I predict would happen is that we would just plateau out at the temporal focus achieved by time reversal. So that was the work done for the regularization, and we were seeing exactly what we had predicted theoretically. Now to the really cool stuff, the multi-source experiment. The whole reason we had this set up with 3 embedded transducers. So what we wanted to do now is we want to emit a source wave field from these embedded transducers at different times, having them interfere with each other, record it at a single receiver again. All of these experiments were done for a single receiver. Record that signal, apply both time reversal and deconvolution, and then back-propagate it physically into our concrete block, and now turn every single of those embedded transducers into a receiver. And we'd expect the wave field to focus at different times at different transducers. So this is the recorded data we got from emitting those source wave fields. You can see the 3 distinct source wave fields in this recorded data itself. Now we applied time reversal and deconvolution, and here came the first test. We were worried that when we would apply deconvolution, that due to the crosstalk of the 3 sources, we wouldn't even be able to see the distinct 3 source wave fields. This is what we got for our calculations for back-propagating signals. In top, in blue, is shown time reversal. In bottom, in red, is shown deconvolutions, back-propagating signal. You can note that deconvolution does still show distinctly the 3 source wave fields. It's not kind of hidden in between all the crosstalk effects of the 3 sources acting between each other. We now take these 2 signals and physically back-propagate them again from that surface receiver, turning that into a source. We then record it at those embedded transducers themselves. And this is those wave fields we recorded, where each column represents a separate transducer. So the left column is transducer number 1, or source number 1. The right column is source number 3, our 3rd transducer, the one that was oriented differently from the other 2. Now there are quite a few notes to make about these results. Firstly, most excitingly, deconvolution works for multiple sources. You can clearly see that we're able to focus the wave field at the correct transducer at the correct times. Now another thing to point out, you can note that energy of this wave field being back-propagated into our concrete block is focusing at different transducers at different times. For example, on our first transducer, at 3 milliseconds, you can see some kind of energy trying to focus for both deconvolution and time reversal. This is really actually the wave field trying to compress at source number 3 at the 3rd transducer, which had generated that wave field. Deconvolution appears to try and suppress more of that energy, thus saying, in other words, we're able to compress the wave field better at our 3rd transducer because we're seeing less energy at transducer 1 and 2. Now another note to make is that source number 3, our 3rd transducer's temporal focuses for both time reversal and deconvolution look dramatically different from the temporal focuses achieved for transducer 1 and 2. And like I had stated earlier, this 3rd transducer was that one transducer oriented orthogonally to the other 2. It was oriented in such a way that its wave field was propagating directly to our receiver, whereas the other 2 weren't. And so we were recording more energy, and thus when we back-propagated, more energy would receive that and be less decayed out due to scattering and things like that. So you can note that the temporal focus achieved, the maximum amplitude of that temporal focus for source 3 is relatively higher than the rest of the amplitudes for the rest of the time being shown. Whereas for our 1st and 2nd transducer, you can note that the maximum amplitude achieved relative to the other energy or the other amplitudes over the rest of the time is much lower. So finally, in conclusion, deconvolution is robust. It improves temporal focusing, and it's able to focus a wave field due to multiple sources. Finally, there's no significant increase in cost. It's a very simple method designed to improve the temporal focusing capabilities, nothing else. In conclusion, I'd like to acknowledge Los Alamos National Laboratory for doing this joint project with me, BOM Research Lab, and specifically Ernst Niederleitinger, who really worked a great deal with me in the lab on this whole project and was a great colleague to have. The Civil Engineering Lab at Mainz for allowing us to actually run this experiment there, even though we're a geophysics group. Of course, you all, the CWP sponsors, for making this project possible, and the CWP faculty and students. Thank you.